So we're going to. This is your not so home office Soho hacking at Pwn2Own, with me, McCaulay, Hudson, and Alex Plaskett. In this talk, we are going to cover our experience at Pwn2Own Toronto last year, specifically covering the router vulnerabilities we identified and used during the competition. So the talk overview, we will begin with the device reconnaissance of the routers, which will cover retrieving the firmware from the vendors, capturing traffic on the devices, gaining a shell access to each of the routers, and then enumerating those routers to gather as much information as possible. Then we will cover the specific vulnerabilities we identified and used as part of the competition, and then cover the Soho mashup, which was a new category to Pwn2Own last year. So who are we? We're the Exploit Development Group, NCC Group, made up of Alex, Cedric, Aaron and myself. As you can see, we have quite a variety of expertise, and EDG exists at NCC to quantify real-world impact, feasibility and risk to our clients, and to mimic real attacks in our clients' environments with high-end capabilities. So what is Pwn2Own? It's a research competition held yearly by 0 Day Initiative, who are owned by Trend Micro. There's multiple different variations of Pwn2Own throughout the year, targeting different categories such as industrial control systems, virtualization, browsers, desktops, and the one we did, which was mobiles, printers, routers, and other embedded devices. ZDI purchased these vulnerabilities, and then provide the vulnerabilities directly to the vendors so that the vendors can issue patches and release new firmware updates. The Soho chain, the new category, requires compromising a router on the WAN interface and then pivoting in the network and then compromising another device in the LAN interface, such as a printer. And all the vulnerabilities that we're discussing in this talk have been patched now. So there's quite a lot of rules within Pwn2Own which restrict some of the vulnerabilities that are allowed to be submitted. For example, you're not allowed to have any user interaction during the attempt, so anything that requires like clicking a pop-up dialog or anything that involves users is not allowed. You have a maximum of 5 minutes per attempt and a maximum of 3 attempts per device category, so that can restrict some of the vulnerabilities that you can submit, for example, if they're unreliable or very time-consuming. Each contestant can only attempt 1 chain of bugs per device category. And a device category specifically is usually compromising a device and getting a root shell. In the case of a router, there's 2 different entries you can do, one for the WAN interface and one for the LAN interface. So you can only submit 1 bug chain, for example, for the Netgear LAN interface. There's different rules depending on the device category that you're attacking. For example, no reboot is allowed during the attempt, but you can reboot the devices before the attempt. The order in which you attempt is drawn out of a hat, and this determines like how much money you can get from the competition, because the first contestants to compromise a device get the full amount, and then thereafter it's reduced. And no technical details are allowed to be disclosed until the vendors have patched the issues, as they are 0 days. And EDG primarily focused on attacking routers and printers with the sole aim of the Soho chain, as that was the highest amount of reward money. So these are the specific routers that we attacked in the competition. We have the Netgear Nighthawk, the TP-Link and the Synology routers, which are consumer routers, and then we have the Ubiquiti router, which is a small business router. These routers are pre-selected by ZDI a couple of months before the competition starts, and they're often the latest model router for that particular vendor. So on to the device reconnaissance. We can start off with downloading the firmware. Often you can straight download it from the vendor's website with no registration required. The firmware is not encrypted usually or obfuscated in any form, so you can just extract the file system using binwalk. Once you have the file system of the router, you can analyze any plain text source code like bash scripts, HTML scripts, etc. You can reverse engineer any of the compiled binaries on the within the router using, for example, IDA, and you can also check the security properties of each binary, such as if stack canaries are enabled, if ASLR is enabled, etc. And this can determine how easy or hard certain vulnerabilities are to exploit. We then go on to the network traffic capturing. So for this, we captured the network traffic from 5 minutes after booting and during boot, because that's basically a time limit on the competition. And we dumped the traffic from all the different interfaces of the router. So from the LAN interface and the wireless LAN interface, we just connected the router directly to our PC and then dumped the traffic using Wireshark. However, for the WAN interface, it was a bit more of a complicated setup. So we required a second router, which we've called the capture router in this diagram. The capture router we need a shell on, and the TCP dump utility. The capture router is connected to the internet and our computer, and then the target router's WAN interface is connected to the capture router's LAN interface. We can then run TCP dump on the capture router to dump all of the WAN traffic from the target router. And that's just a diagram of that setup of the two routers. The main reason for this for the WAN interface is because often on the target router there's no services on the WAN interface. So the primary attack surface is any data that is coming out of that interface that we can potentially attack to go back into that interface. And for the competition, you can assume you're just one hop away from the device. So that you can control, for example, DHCP. So if there's any vulnerabilities within the DHCP integration, you can attack that. So we want to get a shell on each of the routers, and this just to run, for example, debuggers like GDB for viewing processes, etc., and gathering information from the device. The way to get a shell on the routers completely differs depending on the router itself. So, for example, the Synology and Ubiquiti routers, both by design, allow you to enable SSH with the administration port. So that's implemented by the vendor. You have the Netgear router. The vendor's implemented a hidden backdoor, which runs on UDP port 23 and expects you to send a packet which contains the router's MAC address, IP address, and password. The packet is encrypted using a hard-coded encryption key. However, you can get that encryption key from the binary from the firmware that they let you download off their website. The packet, once you've sent it to the router, will enable your IP address in the firewall rules to allow you to access Telnet on port 23. So then you can just Telnet into the Netgear router and get a shell. There is existing public tools which allow you to craft this packet. However, they work for older models of the Netgear router. And as this is the latest model, the Netgear have changed the packet slightly. And now that they expect the admin password to be sent as a SHA-256 hash instead of as plain text. This sort of attack method isn't eligible for the Pwn2Own competition though, because it does still require the admin username and password of the router. Onto the last router, which is the TP-Link router. This didn't have a front door or really a hidden backdoor that we noticed, so we went with the hardware route from support from the hardware team at NCC. For this, we required resoldering the TX and RX lines as they were disconnected on the board, and then soldering on a UART pin header. Again, this isn't eligible for Pwn2Own as it's a hardware attack, but it allows us to get a shell on the device so that we can run debuggers. So now that we have a shell on each of the devices, we can begin enumerating information from those routers, such as what processes are running, what services are listening, Any firewall rules that are in place to prevent certain services on specific interfaces, environment variables and protections such as kernel ASLR. And then to increase the attack surface against the routers, vendors have to publish open source code, which is licensed under the general public license. So often vendors will modify open source code to implement their own features or to patch CVEs themselves. So this is useful because as you can see with the Netgear and TP-Link websites, you can download the source code. There's no reverse engineering required for this, and you can still find vulnerabilities within the routers. The vendors patch publicly known vulnerabilities but may patch them incorrectly, or they may introduce their own vulnerabilities within their custom features. Again, on increasing the attack surface, each of the consumer routers contain a mobile phone app. The mobile phone app lets you control, receive and transmit data to the router. Often it works on over the internet as well, over WAN. And on the LAN interface, many of these implement a custom service listening on the router. So we can use the mobile phone apps to intercept the data that they send to the router to determine how the protocol works for this custom service, example requests, and also reverse engineer the apps themselves to find that information. There was a group of us, but we only had a couple of months to do all this research, so we spent some time developing some custom tooling just to help increase the speed of research. So this is an example script we built called decalls, which, given a firmware and binary, it will analyze the binary and all dependent shared libraries, use it under the hood using Radar 2. It then provides a list of call paths for specific symbols that you set. So in this case, we are looking for popen, system, and execv. It then pulls out the call paths to those symbols. So in this case, it's looking for any low-hanging command injection vulnerabilities. Anything more complicated that uses, for example, like dynamic code execution, this wouldn't pick up, but it's good for finding a quick low-hanging fruit. And again, as there was a group of us over different time zones, we needed to share the reverse engineered code across all of us. And for this, we used both IDA Teams and Jidra's version control system, so that we could push and pull and commit the different reverse engineered code between each other, which was pretty good. So on to the vulnerabilities themselves specifically. We found multiple vulnerabilities, in some cases on both the WAN and LAN interfaces. We gave them all a code name just to help us remember what each vulnerability was, because in the end we had quite a lot of submissions for the competition. So starting off with the TP-Link on the LAN interface, this vulnerability is called mesh-adjacent, and it exists in a proprietary TDP protocol built by TP-Link for their TP-Link mesh Wi-Fi technology. It listens on port 20002 on UDP, and the primary source of data transfer is in an encrypted JSON payload. But again, the encryption is just using a hard-coded encryption key, which you can extract from the binary that you download from their website, from the firmware. There is a traditional stack buffer overflow in the handling of the JSON one mesh support version key. And the protections in place on this binary are that there's no stack canaries enabled, there's no ASLR on the binary itself. However, ASLR is enabled on the library and on the heap, and NX is enabled. There were some complex constraints with this particular vulnerability, and overcoming them is quite difficult, so it's quite heavily summarised in this talk, but there is a full blog post there that you can read if you're interested in more. So for this vulnerability, code looks like this. So this receives a JSON string as the packet body, and then this string is passed to the CJSON pars with len function call, which is in an open source project called CJSON. The code then retrieves the data object from this JSON object, and then the one mesh support version array is retrieved from the JSON, the data object, into the one mesh support version array variable. The code just validates that this is a JSON array, and then it retrieves the array size. And then the code does a for loop over this array size, and it retrieves the ith item from that array into the one mesh support item variable. The code validates that this is a number, a JSON number, and then it casts the value to an unsigned byte and stores it in the shared memory client structure, one mesh support version, which is a fixed array size of 32 bytes on the stack. Therefore, by supplying an array size within the JSON payload that we can control of more than 32 bytes, we can begin overflowing the stack. And because there's no bounds checking on this function or prior to the array size that we provide in the JSON. So this is the stack layout. The corruption occurs in the shared memory client structure at the top, and then we corrupt all of these various variables in this order until we eventually corrupt the return address. Specifically though, we corrupt the one mesh support version array CJSON pointer, which if you look in the previous slide on the CJSON get array item, that pointer is passed to get the next item in the array. So when we corrupt this pointer, we need to make sure that it still points to a valid CJSON pointer that contains the remainder of the overflow to continue. The code also corrupts 1 byte of this pointer on each iteration. Therefore, we need to ensure that we have 4 valid pointers, 1 pointer for each corruption of each byte in memory that we can point to in order for it to continue the buffer overflow and eventually overflow the return address. So here's an example JSON payload that causes a seg fault within the binary. So we fill various variables up, overflowing the stack until we reach that one mesh support version array pointer, and then we set it to a maximum address value so that when that get item function call occurs, it performs a dereference on that function and triggers the seg fault. So to overcome the pointer overwrite issue, we need to be able to place CJSON objects in the heap memory that we can control in order to overwrite the pointer to valid CJSON arrays. And to do this, we need another vulnerability in this binary, which exists in the slave key offer function, which is a different action, but it still receives a JSON payload. This function parses the JSON in the get packet body length, the CJSON parse with length function, which allocates CJSON structures in the heap. The code then checks that method exists on the CJSON string, and that it is a string, and that it equals slave key offer. However, if any of them conditions don't meet, then it returns -1 without deallocating the parse CJSON structures in the heap. Therefore, we have a memory leak when that specific condition occurs. If that condition didn't occur, it would reach the end of the function and call CJSON delete, which would correctly deallocate the CJSON structures from the heap. So we can trigger this function call with an invalid JSON request that does not contain the method key in order to allocate the CJSON structures on the heap from the JSON string we can control. So this is a diagram of the memory layout for the vulnerability. So we begin by spraying the heap using this memory leak function so that we can control the CJSON structures in the heap, and then eventually towards the end of the 5 minutes for the competition, we execute the trigger payload, which will begin the overflow and corrupt that pointer to various different pointers within the heap, which we sprayed using the memory leak. Once the final byte of that pointer is corrupt to a valid, and it still remains to a valid CJSON array in the heap, the overflow then continues, and then we can overflow the return address and then get code execution using the traditional Stack Overflow way. So this is an example JSON string that we spray on the heap. We hardcode the various addresses of the pointers, which will exist within the heap once we have sprayed enough of these requests. We then eventually overwrite the return address with the ROP gadget, pop R0 LR, and then BXLR. This will pop the next argument off the stack into the R0 register, which in this case is the system arg pointer, which just points to another string in the JSON request, which is the command we want to execute, which in this case is LED CLI USB_twinkle, which just triggers the USB light on the router to flicker on and off. The ROP gadget then pops the next address off the stack into the link register, which in this case is just the system function address, as that exists in the binary. As no ASLR is present in the binary, we can just hardcode that address. And then the ROP gadget triggers the jump to execute LR, which is the system command, with our system string. So showing this as a video, let's see if this works. We begin by spraying the heap. We only have a 5-minute time limit for the competition, so we use, I think, about 4 minutes 57 seconds to spray the heap with as many JSON structures as we can, and then we trigger the exploit to perform the overflow, which causes the USB light to flicker on and off, which is enough proof that we can get code execution for the competition. Now I'm going to hand over to Alex to continue with the remaining vulnerabilities.
Yeah, thanks, McCaulay. So McCaulay's talked about the TP-Link. I'm now going to talk about the rest of the vulnerabilities which we found on the Soho category at Pwn2Own. So the first thing is the Netgear WAN. So we started looking at the binaries on the Netgear device, and we found a binary which was called PU-CFU. It was basically for performing firmware updates on the device and checking to see if firmware updates exist based on, say, the current firmware which is running on the device and what is available. So we reverse engineered that, and we found that it connects on boot. It basically makes a connection to this devcom.up.netgear.com. So looking at the code for this, you can basically see that the first thing it does is it makes a call to the this get check firmware function, which makes a request to the back end, to the server side, to check to see if a firmware update is available. I'm going to go into each of these functions in depth after I cover the kind of overview first. But then it takes this response back again, and it sprintf it into a buffer. And then it calls set file value to actually handle the data which it receives from the back end. So the question is, what does this get check firmware function actually do? It basically makes based on some of the parameters on the device, like the current firmware version, the region, and so on, it'll parameterize this request, and it will call into the firmware check API function. So the firmware check API function, all it does is it constructs a JSON request. It fills in the different parameters to construct the JSON request, and then passes it on to the curl post function. So the curl post function is what it sounds like. It's using curl, and it's posting to the back end to post the data. But this was our first vulnerability, because Netgear had basically just disabled SSL verification by setting the curl options to disable verify host and verify peer. So that just means you can man in the middle of the SSL, and using, say, self-signed certificates, you can just impersonate the backend server or intercept the traffic and provide your own response. So what happens when the data comes back again? And then basically it'll parse the this now could be attacker controlled JSON and then act on this data. And there's a key within the JSON data which comes back again, which is the URL key. So this would normally be like a URL to download a firmware update or something. So looking at the code, it basically passes this on to the set file value function. So we control the URL key, which is because of the SSL vulnerability, and we control the full JSON response. It basically takes this URL key and then constructs a string to sed for a command which it's going to execute, and then uses sprintf to construct the command, and then passes this on to Pwn2Own. So just using %s there, then this basically means that the string is vulnerable to command injection. And if we can basically just inject into that, and we've got command injection through Pwn2Own. Pwn2Own is just a wrapper around execv. So yeah, pretty simple command injection there, enabled because they disable SSL verification. So actually, this is what a normal request looks like. This is how you exploit it in practice. Then you'll see the request at the top with the serial number, the current firmware version. That's a legitimate request, one which hasn't been modified. But at the bottom, this is our exploit payload, and we have the URL parameter, and we can just inject in a single quote, then a semicolon, and just start a new command. And yep, straight up command injection there. So here's a video of this exploit actually running, and compromise. So as McCaulay was saying, we're allowed to be one hop away from the router for Pwn2Own. It doesn't have to be across the internet, so we can be a DHCP server. So we're acting as the DHCP server, and then we're providing our own DNS server from the DHCP packet, and then using self-signed certificates to impersonate the back end, like exploiting the command injection because of the SSL weakness, starting telnet on the device, and getting a root shell through the WAN. So there's another WAN vulnerability. So the next thing was looking at the LAN side of the device. Now, the LAN has got a lot more ports open. Like WAN doesn't have any ports open at all. It's mainly just outbound connections. But on the LAN, there's quite a few different services running. But we actually found a binary which was called PU HTTP sniff. It does what it sounds like. It sniffs HTTP packets. And so that was kind of interesting to us. We were like, well, why is it sniffing HTTP packets? Why doesn't the web server just handle these HTTP packets? But it's using the net filter subsystem to basically intercept these packets before it reaches the web server. So on port 80, it injects in a bunch of Linux kernel modules for the net filter subsystem to start the subsystem from running. It sets up some rules, some IP tables rules to perform packet forwarding and like interception of the packets. But ultimately, it implements this function we've called this handle packet when we were reverse engineering it. It wasn't actually named that in the binary, but it was handling packets from the kernel through net filter, and it was acting on data from the packets. So it takes out some data from the packets. We're like, okay, what does it do with it? And we found out it passes the data in the packets to a function we called exec command, because it looked like it was just executing a command based on some data in the packet. We're like, that's pretty strange. But actually reversing it, it takes the user agent out of the packet and then tries to construct a string to map one IP address to a user agent and maintain a table. But they hadn't sanitized the user agent, so there was no validation on the user agent. And because the way they were using string scanf and sprintf, you could basically you could have command injection there as well through system. So you can basically, it's another command injection. So that's how we exploit this. You can basically see the user agent at the bottom, we have like a fake user agent. Then we just do speech marks or double quotes. Then we do like start our command and semicolon, and we've got command injection again. So this is our exploit running for this. And what this is doing is, it's basically just sending the user agent, sending a straight GET request with the user agent in to exploit the command injection. And we're uploading we're uploading BusyBox to the device. We're setting like IP tables, firewall roles up, and starting telnet and getting a shell. So again, another root shell on the device from the LAN perspective this time. Now we're moving on to another manufacturer this time. Now we're moving on to Synology. So we started looking at the Synology from the WAN perspective. McCaulay spoke briefly about DHCP before. DHCP is one of the protocols on WAN, which, because routers like over the WAN port, they need to ask for IP. They can be set up to ask for IP addresses. So configured in DHCP mode. So we were analyzing the DHCP client, which was running on the router. The DHCP client, which was running on the router on the Synology, it's an open source version. So we had it's slightly modified from the open source version, but we had a very similar thing. Like Synology had made very few changes to it. So we downloaded the code for this, and we started examining DHCP option parsing part of the protocol. So DHCP options are like the key way of a DHCP server transmits data to the DHCP client. That's how the protocol works, and option parsing has been a common source of weaknesses on routers before. So we were examining this, and basically we found out that the certain parts of the options, so the DNS, so the host name, domain, and NIST domain and root path, they can all be provided by the DHCP server side. So but the interesting one for us was the domain name which gets passed in the packet. We found out that this wasn't actually sanitized at all. So so this basically gets set to be an environmental variable called domain, and then a script is DHCP-CD, the DHCP client daemon, executes a script when the interface is brought up. So when it receives an IP address, and it executes this using DHCP-CD. And then with this file called dhcpcd-eth0.info. So our domain name is getting propagated to this script, and it's getting propagated to the host info, the first argument to this script. So $1 in this case. And as you can see in this bash script, it's just sourcing the host info, like with no sanitization again. Like they're just like straight up bash injection there again with no sanitization. So we've got kind of another command injection or another bash sourcing vulnerability. So to actually exploit this in practice, then we would set up our malicious DHCP server, and the DHCP server would be allocating, it would have an IP address range, which is allowed to allocate IP address leases for. But we'd have the DNS names, servers, and domain name. But in our domain name parameter, we'd use ignore to basically terminate the command, the previous command, and then we're just setting an environmental variable edg equals hello world to prove that we've got code execution or command injection on the router, and then touching a file. So here's a demo of this, exploiting this in practice. And so what this is doing is it's basically starting a DHCP server on a malicious DHCP server. It's starting a web server running, which we're hosting our netcat binaries, not netcat, BusyBox binaries, which we're pulling down to get a nice pretty shell. And then we're basically calling the BusyBox and enabling telnet through the command injection. and it gets exploited pretty quick. When the device gets an IP address, we just get a shell instantly, which is pretty cool. So this is giving us root access again through the WAN port. So we've now owned Netgear from WAN and Synology from WAN. So we're moving on to Synology on the WAN, Synology on the LAN. So this vulnerability we've called Forget Me because it's a vulnerability within the forget. It's basically called from the forget password CGI script. There's a local web interface on the device, and that basically has a way of retrieving. Like, I believe it's fair. If you forget your password to the admin interface, then you can just retrieve it. But what it does doesn't really matter because we exploited it. But there's basically it's responsible for parsing HTTP requests, and what this code looks like to parse the HTTP requests. It basically takes out a number of parameters from the GET request and passes them to a function called Syno CGI get remote IP. This is a function which they've implemented for CGI binaries, but it takes if you know CGI, then most things from the web server are passed to the CGI scripts through the use of environmental variables, where the web server sets these environmental variables up. So the environmental variable in this case, there's one called HTTP client IP, and the code basically gets the HTTP client IP and then takes this, assigns it to a variable. Then what it does is it calls the Syno auto block binary. It calls the main method in the Syno auto block binary. Then it calls this Syno auto block check denied function, and eventually ends up at this function called Syno net lookup IP. So the Syno net lookup IP, what it does is, like, normally you would have like a client IP address, which is actually an IP address. It would be like a legitimate looking IP address. But in this case, so it would use SNM printf to construct a command again. And it's just using %s, and there's no sanitization there again. So you can see a trend emerging with these vulnerabilities and these command injection ones. But yeah, so this is basically also like command injection through popen through the NMB lookup command. So to exploit this again, we send a get request to the forgot password functionality. We set the header with client IP in there. We use A, and then we can just use like semicolon, start a new command, our command executing, and then hash to comment out the rest. So yeah, that's Synology owned from the LAN perspective. There's a demo of this as well. So in this case, we had to, even though the vulnerability was quite straightforward, we had a problem with bad characters, and our payload had basically we had to avoid some bad characters for the exploit. So what we did was we started a shell listener on 31337 and our HTTP listener on 8080. And exploiting the command injection, we echoed into a file first with the characters which we were allowed as hex encoded essentially, and then wrote a file on disk for that. And we did that to call a Python script. Whoops. Start again. And we did that to basically call a Python script, which has the Python script basically does a reverse connect back shell to our system, and then we obtain a shell through the Python, through the reverse connect back. And we've also got a root shell again from the LAN perspective. So that's another vulnerability. So finally, the Soho smash up. McCaulay talked about this briefly, but this was a new category of in Pwn2Own, which hadn't been, which didn't exist previously. They just introduced it last year. And there's two stages to this category. This category as well, it was worth $100,000. So it was a good one to go for because it was, because the routers are only kind of worth like 20,000 each, like separately. So it's obviously, but it's a lot more challenging because you have to have multiple different steps. So the first stage to do this, then we would have to attack a device through the WAN port, in the initial stage. As you can see, there's our routers, so the TP-Link, the Netgear, and the Synology, which we might have WAN exploits for. But then there's also 3 different small business edition routers as well. So there's Cisco, the MikroTik, and the Ubiquiti Edge router. They're also included as part of the initial stage. So once you've got code execution on the initial stage, then you have to use that to attack devices on the LAN. And the LAN stage is they call it the final stage, but there's things like the Amazon Echo, Google Nest, there's NAS devices on there's printers, there's like Meta Portal and so on there. So this is what it looks like from a networking diagram perspective, just to make this clear, so the attacker PC will attack the target router through the WAN, get code execution on the target router. Once they've got code execution on the target router, attack the other device, the second stage on the LAN port, which is connected. So in our case, we chose a printer. I'll tell you why in a second. So the actual exploit selection for this was pretty important. We had WAN exploits for the Netgear and for the Synology, and I reached out to ZDI. I was like, "Hey guys, is it possible that we maybe do like 3 different Soho chains?" And ZDI were like, "No, that's way too much. Like, you can't do that. You can only do 1." So we basically had to decide on which exploits to choose for this. And we also found a WAN vulnerability on the Ubiquiti, which I'm going to talk about in a second. So we had those to choose from, and then we also had our second stage to choose as well. We had vulnerabilities we had 2 Lexmark remote code execution vulnerabilities in Lexmark printers. And we also had a remote code execution vulnerability in a Canon printer as well. We just decided to smash loads of printers. But so the selection criteria for this was basically like, what is the collision likelihood? Because these vulnerabilities, which we've been finding, a lot of them are like command injection. They're kind of like shallow vulnerabilities. They're not super complex. Then we need bugs which are not going to collide, because each time there's a collision in the competition, the prize money is reduced. We need reliable bugs, like reliable exploit chains, because you only get 3 attempts at Pwn2Own. And if you fail at the first stage, then you won't get onto the second stage. Or if you fail at the second stage, then you basically have to repeat the whole thing over and over again. So it has to work end to end. And obviously if you've got unreliable exploits, memory corruption, then they might fail and then you won't win. And then finally the prize money as well. So the Netgear and Synology, they're worth less prize money as just individual targets over the WAN, but the Ubiquiti was worth more. But we had to make a trade-off to basically decide on which would get us the most for the competition. So moving on to the Ubiquiti then. This vulnerability was in DHCP v6. So not DHCP, not the v4, the IPv4 version. It was in DHCP v6. And it was in some functionality called prefix delegation. I'd not actually heard of prefix delegation before I started doing this research. Like, it does seem like it is used in the real world, and people are actually using this for IPv6 networks. But, yeah, like, I don't know how popular it really is. But so what this does, this prefix delegation, it's basically a way of having, it's similar to NAT. So you can basically have, say, like a range of public IP addresses, and then you can have your device allocating out different IP addresses to other devices which are connected on different network interfaces on the router. Yeah, and as I said, it's fairly niche. Like, we Googled around for this, and there's definitely people running this because we could see them posting questions around configs and so on, but I'd not heard of it before. So the vulnerability itself was in the option parsing, because as a similar thing, it's untrusted data from the server side to the client side, and it was to do with parsing the domain search list. So the domain search list is basically a way of providing domains from, like, a list of domains which are used by the router, and for each of the different domains, then this code, this DHCP6 get domain, it basically loops through each of the elements within the list, and it calls DNS decode on each of these items within the list. So we dive into DNS decode function. You definitely can't see that at the back, and probably not at the front either. But the code is really small. But there's some parsing happening here. But ultimately, what happens is it doesn't protect against like certain bad characters. So things like curly braces, like double quotes or speech marks, then dots, like slashes. You can get all these things through this DNS decode function. So I was like, yeah, that's pretty interesting. Like, where does it go? So what happens is it takes this data and it assigns it to this environmental variable called new domain name. A new domain name environmental variable is there, and it basically it passes this to some Perl scripts, exposes this to some Perl scripts. So this UBNT DHCP6C script calls DHCP v6 PD response to handle prefix delegation response packets, and it takes this new domain name variable, which we fully attacker control with no sanitization really, and then it does like a regex, which the regex just extracts it, doesn't do any like validation there again. And then the Perl script loops over the different elements within the config file. So this obviously requires the router to be set up to use like prefix delegation, because we're exploiting a bug in prefix delegation. But and then so it loops over the config elements. And then if it determines there's a server, and then it goes through the different services. So there's a service, there's something called Slack, which is used for like auto configuration. But there's also different services here. And there's this thing called DHCP v6 stateless and DHCP6 stateful. Now, we looked at DHCP stateless. So there's a function called setup DHCP v6 stateless, which handles that. And it takes our domain name, our interested attacker controlled value, and it tries to build a config file for use on the DHCP client side on the LAN, from the LAN on the DHCP server for the LAN perspective. So what we can do is we can now inject into the config file, which, because what this Perl code here does is the domain name variable is just string concatenation. That's just string concatenation in Perl where you can you don't need to use a plus, you can just use $, and then put the strings together to construct an output string. So we've got config injection in there. So how do we actually exploit this then? Basically, our string is part of the config, but it's in the middle of a string. So first we need to terminate the string to start a new command in the config. Then we can start our injection with a semicolon, but but Perl adds its own. So what we basically need to do is we need to do speech mark or double quotes, then semicolon, the malicious stuff which we want in the config file, and then a hash. But because we're inside of a config file, we're in a DHCP config file, you wouldn't normally be able to execute programs or run things, but turns out DHCP has a command within the config file DSL within the config language for the command, which is just called execute, which is kind of useful as an attacker if you want to execute something. So what we can do is we can make we have some restrictions on this. We can basically, because of the firewall ruling, we can't just start a service running because there's firewalling on the WAN. So we could maybe have dropped the firewall and changed the firewall rules, but instead we decided to do a connect back to our own system, to do this. And we also needed to use a link local address to do the connect back. I'm still not entirely sure why we needed to use a link local for this, because DHCP would give you an IP address, but for some reason there was no routing between the attacker system and when we exploited it, and link local worked fine for this. We also have some constraints on our payload. So we're just limited to 63 bytes, and IPv6 addresses themselves, they're pretty long. So that doesn't give us that much space for an actual payload to exploit this bug. So to exploit it in practice, we basically do double quotes, speech marks, semicolon, execute, then netcat. Ubiquiti handily left netcat already on the router, so we didn't need to deploy it. And did the connect back to get a shell, and commented out the rest of the thing. So that's what this looks like when it's injected into the config. So this is our the chain. That's our stage one of the Soho chain. We've now got a shell on the Ubiquiti router, but we need to compromise something connected on stage two, so the printer. We had a choice between Canon and Lexmark for stage two, but we had some challenges. We'd written our original exploits in Python, and we didn't really want to be recoding a bunch. These were memory corruption exploits for our stage two, and we didn't really want to be recoding everything in C because it would have taken us weeks. So basically the choices we had were we could drop a static Python interpreter on the device, or we could re-implement it in C, which we'd kind of ruled out, or we could proxy the stage two through the stage one, set up some kind of tunneling through the router. But we just went with the easy option, which was build a static Python interpreter and for the architecture of the Ubiquiti router and deploy that to the router. And then that allowed us to launch our Python exploits from the router itself. So if we look at the code, so if we look at the demo, then basically what this is doing is it's starting DHCP v6 server, which is waiting for release to be assigned. Then it's performing the injection there. We're in it. We're dropping the firewall rules where we're doing a connect outbound, enabling telnet, and then finally netcatting in, and that gets us a root shell on the Ubiquiti. As part of our exploit code for stage one, we automatically deploy the stage two Python scripts to the router. We just push them up and deploy that exploit. So the exploit's already on there. Then we're doing /run stage two, which is running our stage two with the IP address of the printer on the LAN, and exploiting our printer vulnerability from the LAN perspective. And I'm not going to talk about the printer vulnerability today because that's a whole different talk. But and that's also getting a shell on the Lexmark printer and executing code on the Lexmark printer. Thank you. So, conclusion. Basically, we didn't win overall. There was a lot of competitors in the competition. There was something like 42 different entries to Pwn2Own in the embedded categories. So there was a lot of teams, a lot of really good competitors there. DevCore won overall, but our team, we came third, and we were pretty happy with that based on what the work we'd put in and us just working together as a team and the vulns we found. So, and we won 78,000 from this. It's quite nice. So in conclusion, we had too many router collisions because there was so many entries to the competition. There was a lot of successful entries, but we had we had 4 collisions out of the 6 successful entries. We had 2 patched prior to the competition, which McCaulay blogged about, but there was tons of entries. It's a bit concerning that the vendors are like still having these low-hanging fruits, these command injection vulnerabilities still within their code bases. Like, and why aren't they finding them if loads of other people are finding them and colliding? Like, surely there's obviously a problem with their SDLCs or whatever they're doing, but maybe, yeah. But the Soho chain itself, that didn't collide. That was the one we really didn't want to collide because we'd spent a lot of time on there. So our Soho selection of exploits, it paid off. I just want to say thank you very much to all the people who have done router research. Like, we definitely weren't the first people to do compromising routers. Like, there's tons of router security articles out there, and I did a Twitter post, like a massive Twitter thread about this. And yeah, so just thank you to all these people who have done stuff before who helped us determine what the attack surface was. So are there any questions? If I got time, 3 minutes, yeah.
All right, I think we can do one question before we have to move on to the next talk. I see a very enthusiastic question over here, so if you can get the mic here at the front.
So why did you choose a printer as a second stage?
So the mic is coming, so we can also hear for the recording.
So why did you choose a printer for the second stage?
So the question is, yeah, why did we choose a printer for the second stage? Basically because we had tooling already developed for attacking the printer. We did Pwn2Own the previous year, attacking just printers. So we already had our tooling to find bugs from that. So we just reused existing tooling basically. But yeah, good question. And we'll probably do a talk later in the year about the bugs which we used for the printer on the printer side. So yeah, thank you.
All right, thank you very much, McCaulay and Alex.